mind that after 2 years, this is the first in-person talk, and for me, this is the first seminar. So seminar in the sense that I'm talking in front of, for me, it's a wider audience. So most of the time you go to conferences, you have similar topic people, and then they have at least certain already given or talked about your topic, and you repeat there. Here I'm finding that, okay, audience are different. So I have kept it bit basic, simple. As well as I have shared the YouTube link on my social media. Some of my relatives are also listening to it, no matter they understand or not, but I just want them to give some glimpse, because obviously they can criticize me. So there's such that though they don't have astrophysics knowledge, but they have the ability to criticize me and appreciate me. So you have to provide them something. So shall we begin? So I've started with a simple picture of Milky Way. So we know that we live in a galaxy called Milky Way, and from many rural areas, even in there, you can watch this dusty lane, which is our own Milky Way, and I have been doing from my place, hometown, which is getting worse. Have gone worse scenario in last 5 to 10 years, because you have everyone is having electricity, you have huge bulbs on then street lights and everything. So begin with Milky Way. So we have a galaxy called Milky Way. This is a spiral galaxy. So in universe there are billions of galaxies outside the Milky Way. They are different in size and then shape, masses, and along with that, these galaxies are just gravitationally bound system, where you have again huge number of stars. You have gas and dust. So as I said, that there are different types of galaxies depending on the shape and the masses and everything. Depending on their activity, nuclear activity, we divide these galaxies as normal galaxies and active galaxies. So when I say normal galaxy, we say that most of the light what you are getting from this galaxy is from stars. And when we say active galaxies, the total light cannot be explained by the number of stars they have. So then you have to incorporate some extra source, and that extra source can be, like, people have thought of accreting supermassive black hole. And when I'm talking about supermassive black hole, the mass range can go to 10⁶ to 10⁹ solar mass, right? So how these two galaxies look different in spectra. So as you have, like, from sun, we get spectra and lines from different species. Similar way, the combined light, when we detect from galaxy, we can have a spectra. So one, can I have pointer? Okay. So this, yeah, sure. So this normal galaxy, most of the time you will have absorption line in your spectra. So absorption line, maybe in solar spectra also you have, because you have the atmosphere, cooler atmosphere in front, right? But when we say active galaxies, you have several emission lines. So emission lines with several kilometer per second velocity, which means that you have a cloud which is moving with such huge velocity. So say, like, we have velocity range from few hundred to few thousand kilometers per second. So what it says that you have a cloud which is moving with 5,000 kilometers per second. Now, as we know from our basic, say, like, grads and undergrads, that you need a very massive body, that gravitational power, so that the cloud or whoever it is can move with certain mv²/r, right? So from those aspects, people have understanding that at the center of the galaxies, these galaxies, we have some mass which is 10⁶ to 10⁹ solar mass, and we call it a supermassive black hole. And when this supermassive black hole, so from the name we know that black hole, supermassive black hole has such a power that it cannot allow even light to escape, right? But when I'm saying that galaxy is luminous and much luminous than the what stars can provide, then what we are talking about. So here we call it active galactic nuclei. So basically this massive black hole is accreting the matter, and before falling to the black hole, it emits, because it has to lose its angular momentum and energy. So it emits a huge amount of light, right? So that actually that is called as active galactic nuclei. And this is just the artistic view of active galactic nuclei. So basically you have a central supermassive black hole. Around it, you have a crescent disk, and then what we call as broad line regions. So these are clouds which are moving near to this black hole, and broad line regions in the sense that they're moving faster because they're closer to this massive body, and their velocity range can go to 1,000 to 5,000 kilometer per second. And later you have narrow line regions, which is a little further. So there the velocity range have below 1,000 kilometer per second. And this information we get from spectra. So you get the species, say like H alpha, H beta, and you get the width of the line, and then you can infer that where these clouds are present, right? And then again from the, I won't go into details of this. So this is called torus, because from AGN, sometimes people have observed only a narrow line region, sometimes people have observed both narrow and broad line region. So then what defines it, and how you will be explaining it? So people say that, okay, something is there which is obscuring the, so if you are looking at certain angle from top, then you can get both. If you are looking at it from perpendicular, then this broad line region will get blocked by the torus. So you will get only narrow line regions or narrow emission lines. And apart from that, you have radio jets. So these are called jets. You must have seen like some of the beautiful pictures from Galaxy Center. These jets can go, so these are like bipolar structure. It can go from parsec to megaparsec. Sometimes from galaxies, it can go beyond galaxies. So suppose we have 30 kiloparsec of Milky Way, it can go beyond of that. So these are radio jets, and there are like several aspects people are trying to infer and understand from AGN itself. So this next slide, what I have here, yes.
All supermassive black holes have an AGN or not?
No. So we call AGN when the supermassive black holes are accreting. Sometimes it can be potent, so it cannot. It can be silent, so, or it have what we call that supermassive black holes are not always have material to eat.
So basically, it depends on whether you have distribution of
matter around it or not. So this next slide I have kept to give a brief and broad motivation that what we do and why we do, why should we care about AGN and galaxies. So what we have that suppose you have this black hole mass from different galaxies, and then you have stellar velocity dispersion. This stellar velocity dispersion comes from stars. So the star is on the disk of the galaxy, and supermassive black hole is sitting at the center of the galaxy, and this has very tiny scale. Now the fact is that both these quantities, they correlate. So the question comes that how this tiny person is talking to the rest of the galaxy. We don't see any direct evidence as such. So there are few, but then this comes to question that for many galaxies, several galaxies, when people have plotted this, how these two quantities can be correlated. So these questions remain, this is an open question, this is an open question, still an open question, and people are trying to infer that how could a large number of different galaxies, this tiny person is talking to the rest of the galaxy for 30 kiloparsec or 20 kiloparsec, whatever size we have for galaxy disk. So this quantity comes from the galaxy stars, which is on the disk, and this quantity comes from the center of the galaxy, which is supermassive black hole.
So can you clarify a little bit about what do you mean velocity dispersion? Is it some, you have a radial velocity?
Yeah.
So what is dispersion?
So dispersion is like the way you have stars, and then stars have a radial velocity, and then the total star, when you get the spectra, so this total star have this how to call it, um, just a second. The total stars can move, you have both sided radial velocity, move away and towards you, but then the total, whatever spectra gives you, is that width of the spectra from the basically from the absorption line. So you have that absorption line. So basically your whole line can be blue shifted and red shifted, right? So this and you, for the individual species, you have certain central velocity. So from that quantity, you get the velocity dispersion. So this basically, people are saying that has connection, or maybe the found connection between this velocity dispersion and black hole mass.
So basically, one can interpret that as the departure or the alteration from the normal orbital velocity that we expect given a
mass at the center. Yes, yes. And the second, another plot I have put here is that this is for redshift. So what we have here, that the star formation rate density. This is the star formation rate density per megaparsec on the sky or universe, and then with redshift how it has evolved. So redshift, in the sense we are looking back, right? So higher and higher redshift means we are looking back in the history. So this is the time scale. We are at 0. So we are at redshift 0, and more higher redshift in the sense that we are looking back. So whatever we are questioning or whatever we are researching is about to understand that how universe has evolved from past to present, right? So how everything began, and then how things have evolved, and why we are here, and how we have reached here. Yeah, growth also. So both these quantities, star formation rate density and black hole growth, peaks at redshift. So this at present, or it has decreased. So this whole question, a whole understanding would give us that how things have evolved, why that time, what happened to that time, that star formation rate increased. Because you need matter, you need interactions, you need activity, and then what has happened. So obviously we know that, suppose if we believe that everything is, we are going away from each other, from the Hubble thing, right? But then why at this particular redshift things has happened in such way which is not happening at present? So this is one question to understand, or reveal the galaxy evolution or our evolution, I would say. So these are the two plots which put the question that how this black hole talks to rest of the galaxy, what happened to redshift 2 and 3, and how rest of the places, rest of the years of galaxies have evolved. So these are the two questions a bigger question we have in our mind. So one way to understand, or one way to infer this, is through galaxy mergers. So if you see, some of the astronomical objects or images, you will see that galaxies are merging. Two galaxies are merging. You must have seen that. So we see that, and we have spiral galaxy, we have elliptical galaxies, and people infer that these elliptical galaxies have come from the merger of two spiral galaxies. Because it has shape and everything, it has gas, and this elliptical galaxies don't have gas. It doesn't have shape. So there are again another kind of theory which I have not put it here. So there are like theories where people say or think that obviously in past merger has happened, small galaxies grouped together, and it has created present day massive galaxies. So this is one another aspect to think galaxy evolution. And people have actually tried to create similar what observation have shown from the simulation, and you can see that there are like two spiral galaxies through different phases it goes, and then it merges and it creates one galaxy. So if you are convinced with the information I have given here, so suppose this is one thing, that galaxies grow through mergers. So there were like past smaller galaxies, through time it came closer, it got merged. Another information I said, like galaxies have central supermassive black holes, right? At the beginning I said that some galaxies are active. Now if we combine these two aspects, say in past two galaxies where both had active supermassive black holes, they merged and we are seeing them at present. Then some of the galaxies should have two supermassive black holes. So this is how this dual AGN things come. That you believe that galaxies grew through mergers, galaxies had central supermassive black holes, and if this had happened for several galaxies, then some of the galaxies should have pair of supermassive black holes. But first we need to start from single to pair, right? And so simulations say that when you have galaxy mergers, there will be turbulence, there will be gas inflow, and once this gas inflow will happen towards this supermassive black hole, the supermassive black hole will start accreting the matter. So then it will become active. So if both the supermassive black hole becomes active, or AGN, we should expect to see a pair of AGN, because obviously we can't detect supermassive black hole. Supermassive black hole is blank. There is no radiation. But when we can infer that there is gas, there will be gas inflow, then it will start accreting matter, and there will be pair of active galactic nuclei. So this is what called dual AGN or binary AGN. So dual AGN is when the separation is large, say like 10 kiloparsecs. And this doesn't have very strong meaning, I would say. It's the literature we use, that when it becomes gravitationally bound, like say like below 100 parsecs, it's underneath that center of the galaxy, then we call it binary AGN. But we're not going into the name of binary or dual AGN. So then this binary or dual AGN, the number of this binary or dual.
Can I ask a question?
Hello? Yeah.
Hello?
When I started my study in 2015, the number of this binary or
Hello, can I ask a question?
Hello? I can hear, but not clearly.
Can you hear me now?
Yes.
Okay, so what is the time scale of this merger for these galaxies? Like typically, how long is the time scale?
Yeah. So.
Can you repeat the question for the
Yeah.
so that everybody can hear?
So if I have understood correctly, you are asking that what is the time scale for this phase, right?
Correct.
Yeah. So then so there are few studies, theoretical and simulated studies. So it goes from 10 raised to around a giga-year. So,
okay, the picture that you have, is it artist impression or is actual?
Sorry, can you repeat?
What I'm asking is that the picture that you have, is this an actual observation or it's some simulation? In the picture that you have in your slide.
What?
Hello, can you hear me?
Yes.
Yes.
So now we can hear you now clearly.
Okay, so what I'm asking is the picture that you have, is it the actual observation or some simulation?
Is it actual observation or simulation?
Oh, this one? The slide I have now?
Yeah, correct.
So this comes from simulation. This is not an actual image, and this is for like the previous image, again from simulation.
Okay. So the reason I was asking, because you're saying the time scale is all of giga-years. So what are the Newtonian values?
Okay, for the simulation.
Yeah.
So I won't be able to answer this correctly at present. because I have not looked into the simulation yet. So in future, I'm planning to collaborate with some of the people where I may get chance to look into it in details and maybe study further. So
the reason I was asking is that if it is a giga-year scale, right? Even if you make a small correction, let's say Newtonian gravity, the result could be different if you use general relativity, for example. But it is not a short evolution. Giga-year is a long year, right? 10 to the 19.
What is it?
Yeah.
So what you're saying is, I think if I understood this correctly, that small correction to the galaxy, they could have an impact on the time scale.
Time scale. Yeah, I think it can.
It will happen. So that's a strong process, right?
Yeah. So that can be there, but
The question is, what fraction of a giga-year?
Yeah, so that can be, and then the whole thing would depend on that at what separation, what is the mass of this individual body, right? That obviously it goes through. It is not that once it gets collapsed, it goes through the several orbit, and several times it passes one another, and then at the end it will get merged. So yes, but what's his name? Gulab. Okay, so I think I will think about it and look into it further, and maybe I'll discuss with you later.
Yeah, please go ahead.
Yeah. So what I was trying to say that when I started this study in 2015, the number of detected dual AGN was very less. So less in the sense that there were like 14 to 15 in number. And then actual motivation is that when you have large number of this system at different separation, then only you can start understanding or using it for statistical purpose and to understand galaxy evolution. You can't do it for one or two systems. And obviously this 14 or 15 system, what people have discovered and found mostly came serendipitously. So it was not that people were looking into it or searching for dual AGN, they were looking into something else and they have found this interesting system. So individual systems are interesting, but to study further or to understand or use it for galaxy evolution, one needs large number of this system at different separation. So how one can detect this system? So these AGNs are very active and very luminous. It emits light in all the wavelengths, right? So suppose in X-ray one can detect this AGN. So to detect dual AGN, and when we are talking about 10 kiloparsec or less than 10 kiloparsec, you need very high resolution. So suppose for X-ray, hard X-rays are concrete evidence for AGN. So one has to look for two pores in X-ray, and to even look into, say, very nearby galaxies, redshift 0.5 or 0.2, you need such high resolution that you have to observe with Chandra. So Chandra is the X-ray satellite, right? But people like us or all of us can't just apply for Chandra and just ask for timing. They won't give. It's such expensive. So then, I mean, basically, you can't just ask that, okay, I just want to observe this part of the sky to look for dual AGN or something like that. They don't have time for us, and they don't have money to continue that telescope in such manner. So, but obviously, some of the discoveries like Markand 739 and 6240, those have come through using X-ray Chandra observation. So obviously people have some of the largest group, they ask for time and they have detected a few. And then from optical also you can detect such system, but you need a spectra of individual system, because optical light you get from stars also, right? So then only you need a spectra where you will have this extended broad emission lines from individual nuclei, then only you can confirm that these two are AGN. And everything goes for very high demanding telescope. Next comes this
this is species on the side, and this two are two nuclei detected in radium, 6 kilopascal separation. And some of the furthest separated binary AGN, so like 7 parsecs and even half parsec separation came from this VLBI radio study. So VLBI is an interferometer which has several bases, like yesterday we had heard of the image of graphic Sagittarius yesterday. So that means very high resolution. And for that, people have combined the radio telescope radio dishes from all over the world. So such high resolution we needed. And similar way, these studies come from say like part of the world, say like the European part or Europe and USA part. Whatever telescope they have, they combine those telescopes. Using the interferometry method, you can gain say like arc-second and sub-arc-second resolution, and then only you can look into these systems. So these are the detections people have found from radio study. Now, as I said that, so these came through serendipitous, right? And but now if you have a motivation that we need a large number of such systems to understand the galaxy evolution, you need more and more detection. Now to detect, as I said, that you can't just ask blindly. So you have to start your sample from, you should have certain indirect signature. So okay, you can convince the committee that okay, I have, okay, these signatures can be explained by binary or dual AGN. So I'm asking for this time and I have a certain percentage of success and things like that. So suppose one of the index signature is that this variability in optical flux. So AGNs are variable. So time to time they change the optical flux, right? And this particular object has 100 years of data. So 100 years of optical data people have, and when they have plotted it year to year, like to time, they have found that around 11 to 12 years there is this flare. This time and assumption here, but when they model, every 11 to 12 years there is this flare. So then try to explain that with this 100 years of data, every 11, 12 years, what is causing this flare? And they came up with this model that you have central supermassive black hole, massive body. You have a secondary black hole, massive body. It goes through this accretion disk every 11 years or 12 years, and then it gives this flare. So accretion disk is a material, right? And a massive body pass through it, so it will give eject some of the matter. Yeah. So then with half period of 11 years, they get this and they try to explain that. But obviously there is no direct evidence. So obviously
inferring material
from
when it gets close to the
black hole,
it gets accelerated, heated up, and then it starts radiating.
Yes. Yeah. So then, so this like, but obviously not everyone has that rich data, right? 100 years of data for many of this we don't have. So this is. Oh, okay. So I used to remember that. Now I don't remember. I used to remember that when I was at the beginning. Now I have, but I no. So this they have build, right? So they have built the data and then they have plotted. It's not like you can say like a point in 100 years. So given date they have put it. So, but it has 100 years. Optical. So still like people are predicting that when this through this model that when this next flare can come,
and then they're trying to observe molecules with different telescopes. Which that's what I was trying to know. So one of the discussion lectures we have that in future if this VLBI system what has observed M87 and see that whether they have or not. And the second index signature one can have is this S or XF radio jet. So at the beginning I said like this agents have radioactive body and have a jet, and due to the presence of the secondary massive body, it pushes. Like we have several other like objects on Earth, but it pushes, right? Because in Earth it's not like just rotating, it's pushes. So the similar way, if you have a massive body at the center, it has jet, and there is the secondary massive body or massive black hole. Due to this, due to its effect, this fan switches. So one explanation can be this. The third index signature is this in this optical spectra. You have double peaks. So optical spectra you must have seen that it has certain peaks. So suppose you have two wavelengths, right? And it is so how it will be moving. So you observe that one is the sunny cluster, one is the green cluster. So then one line will be blue shifted, one will be red shifted. But your instrument doesn't have that sensitivity or resolution that it can resolve individual spectra. So what you are getting is a combined effect. So then one is blue shifted, one is red shifted. So it has from the center, one has shifted to left or right, and one has shifted to the left, right? So then this is another index signature that we have tried to explain with the presence of binary regulation. But the fact is that all these are index signatures. There are like explanations with a single element which can produce similar signatures. Suppose you have this jet in the center, you have ionized medium. So that can also, it can switch to that, and then while emitting this will emit this will have this emission line, one will be blue shifted, one will be red shifted. Because suppose at the 0 point you have jet, so one will from this and one will be coming to this. Again you have material and if it ionize this medium, the line it will emit, it will be blue shifted, it will be red shifted. So the single agent can also explain this. So that's why these are called index signatures. It is not that we are concerning something, but at least starting from this signature, you can ask for self-speciality that I have to simple objects, and at least I'm going to check that the distance is not really. So this is like for my first project, I have used a very large area telescope. So this has again this 25 meter like individual dishes, and they have 34 discs, and this telescope is so large that it's on change. So time to time you can change it. So basically the position you can change. The resolution depends on the maximum distance the dishes have, right? So what VLA facility VLA has that on this field they can change the position of the telescope. So here in a year they have placed two sensors where the position of the telescope they change, and suppose they have named it ERA. So ERA means they are in maximum distance. So then you get highest resolution because it is lambda by d. Yeah, so the telescope is on the land, and then you can move them. Yeah. Mm-hmm. No, so that's the matter. That this maximum resolution, not every science is looking for maximum resolution. They are looking for maximum sensitivity. So they need low resolution but high sensitivity. So there are two things that in radio astronomy we have that the telescope this is position on. Depending on that, we get then it is a harsh radiation, then it is a sensitivity. Then try to look for this radiation. Okay, so a small radiation, you need high high sensitivity. Okay, it depends. Potential, it has frequency and it has potential density, lambda and beta. So then potential GMRT, giant meter which we have a frequency to use, and then there is fixed. It depends on potential fixed. Also, there is this new potential radiation. So they have 325, but 325 at 325 megahertz, the fixed basis will have a low radiation. But then 325 the sensitivity goes up.
Is it fine now? Okay, okay. I need to finish this, and because you people must be getting.
Just for general reference, we found light numbers.
Mm-hmm.
The observation come from there. The given area.
Yeah. So I'll go to my results because I need to show that what I have done while giving the story too. So that's what I have done, like I compiled a sample of 20 double peaked emission line galaxies depending on some certain criteria which I have not put. So they kindly gave me time in 3 cycles, and I observed these 20 objects. So this was not, I mean, when I started, I was like, I'm trying to detect it. And then later, my conclusion said I was trying to see whether double peaks are good indicator for a dual AGN or not. So obviously, your motivation changes with times and years. So what I have, so this is the first image I got, like at 6 gigahertz with, and now I have a look, I mean, made it to look good and looks like a jet. But when for the first time you reduce your data, it takes almost 1 year to starting from when you start writing your proposal and if you get data. So after 1 year, when I reduced this data, these 2 bright spots, right? So I got excited thinking that this is it. Like from first observation, I have detected dual AGN because the number is 15 or 16. So if you can add at least 1, that is going to be huge, and people are going to appreciate your method. But then when I reduce this high resolution, 8.4 gigahertz and then 11.4 gigahertz, your resolution gets higher. Then I found that actually this has a core, center is here, and this 2-sided what we call like jet hotspot. So it's not 2 systems, it's 1 system. It is core and jet hotspot. What interesting, like with that depressive moment, I have found that it has this jet is not straight, right? So it has this S shape. This has this curve shape, and that during this curve shape, then I said like this S or X shaped radio jet, that can be another signature for your dual AGN, right? So along with that, I tried to model that S-shaped structure. So this is another source, SS433, a micro quasar, which is very famous, and people have tried to model that with precession jet. It's a kinematic model. I tried to fit the similar model for my source, and then I try to find that what is the precession period. If it is precessing, what is the precession period? 10⁵ years I have got. And using that precession period, using certain formulae, what people have already invented, you can try to get the separation. So using this period and mass of micro arc second, which cannot be accessible with present day telescope. So there is no way to say that whether it is due to this secondary black hole at 0.02 parsec or not. But there is a possibility that you have this accretion disk of single AGN itself is unstable due to any reason or due to some reason. And this unstable accretion disk can again precess this jet. So there are possibilities. So we have put all those possibilities in our paper. And for other 19 sources, for 3 sources, we have detected these 2 coarse. These are like optical image, and black are your radio contours. But for only one, we could confirm that these two are AGN. For other two, we don't have optical spectra because the radio power falls in between this star-forming galaxy and active galaxies. It's not at the higher end. So the radio power from one single photon, what you detect, if it is very powerful, you can say that only AGN can explain that. If it is low, then a low power AGN as well as a total accumulated power of stars can also explain that. So you need a spectra where you will have again the emission lines which can explain that. So for one source, we have confirmed dual AGN, and for another source, we have S-shaped structure which we are okay. So if somewhere peaks, so you can infer that it should come from this 3 arc-second. But if my objects or these two AGN are separated more with separation more than 3 arc-second, then I can't say that this double peak is the reason for dual AGNs are the reason for double peak. You know that I mean a single fiber has a size of 3 arc-second. So whatever spectra of double peak with double peak I'm getting from this 3 arc-second. So I'm saying the reason is sitting inside this 3 arc-second, but my secondary black hole or the dual AGN, if it is separated with 5 arc-second or 6 arc-second, then this secondary black hole is cannot be the reason for this double peak, right? So then through these studies, we infer that double peaks are not good indicator for dual AGN, and there are like several other studies too which have used other instruments and they have different statistical value. So I have not given any details that how we acquired that, but this is the way I can deliver or infer I mean to you people that this is the size of the fiber, and when you don't get the secondary object inside 3 arc-second, then it cannot be from that. How much time I have? I have time. Okay. Are you people bored? Not sleeping, right? Okay. Okay. Yes. No, that's fine.
Two black holes at one, two clusters separated from each other. Why don't you call the black hole merger committee to look at those regions that these black holes may merge in the near future?
Yeah. So that's what I'm saying, that the distance it has and the facility we have, it cannot look into, it doesn't have resolution of that.
My point is not that. My point is, let's say, what we found, if I find to perceive between two areas, if that is correct, then in near future, these two black holes have to merge. Because if they are rotating just that far, there is no other option other than merge.
They'll merge.
So then we can see it in geos, right? If we find that coming from that area, then your prediction is right that there is two black holes.
Yeah, so that's the thing, that for supermassive black holes, obviously LIGO won't be able to detect that because LISA will be there, right? So LISA, we are expecting that in future or whatever we are doing in future, when LISA comes up, things will be there and we'll be talking, and there will be obviously community which will be looking into this. Yeah. So the other aspect we have is that feedback. So the plot I showed, right, that this black hole mass and velocity dispersion, someone at the center and someone at on the disk. So one is to look into again through mergers and have large okay. Yeah, it's this feedback is another thing we talk, is that suppose I said like black hole
eclipse, right? And yeah, so where was I? Okay, that plot where this black beyond the galaxy and over the galaxy, there are outflows. I have not shown those. So similar like the broad outflows, which I mean, it starts from a supermassive black hole or AGN and it goes to fall into the galaxy disk or things like that. So then these are the factors. So one way I started looking and I'm still looking at merger, how it can impact. So that is still ongoing. So one aspect I looked into the dual AGN, double peak emission line. See? The second one is that, so when this black hole accretes matter, after a certain critical mass, it expels this matter. And the effects of...
Expelling matter must be happening from outside the event, right?
Yes, yes, yes. Yeah, but I won't be able to answer that.
I think
Okay. So now the fact is that you have matter expelling matter through jets or outflow. Then one has to look into that this outflow jets can ionize the medium and increase the star formation. So it's matter from the galaxy. It won't have anything to form stars. If the material is thrown by this outflow, then you don't have anything to form stars. So one is a dual AGN. One is this feedback. Like feedback is mostly related to how much star you have and to see that whether AGN has any impact or not. We have started a study with UVIT. UVIT is one of the 5 payloads on AstroSat satellite, right? And it has this SEG and NEG telescope lens, you can say. And it has resolution which is 5 times higher than the existing telescope or the survey Galaxies we had. So we started a study using 20 merging galaxies, and here the motivation was to understand the stars and feedback effect. For one of the source like Markarian 212, we have combined our previous objective and present objective. So for this source, we have used data from ETLA, GMRT and HTTP spectra to understand whether these two are AGN or not. And data has confirmed that these two are low luminosity AGN pairs at the separation of 6 kiloparsec. And EGIT, it's not very visible, has these 2 clumps of stars, 2 bright clumps of stars that overlap with radial structure. So here we have tried to say that this radial structure, whatever it is, basically these 2 are stationary clumps near to the nuclei. Now if we are detecting 2 clumps, star forming clumps, then there can be connection with central AGN, right? But for other galaxies, we have the galaxy evolution, that how this jet has impacted, why redshift. So basically you take a large number of radio jets, 28, not radio jets, low luminosity AGN. You look low luminosity AGN, the jets are not very, how to say, it's not very concrete, or it's not in a straight line. Sometimes it can be vague. So if we are talking about, say, like redshift 2 or 3, and at present how this jet has impacted, we can't just go with this high power jets, because those are only 20%. Most 80% jets are this low power jets. So you have to understand this low power jet, and that's brought me to my next project. So here I am investigating 28 Seaford low power galaxies, jet with jet, and try to see that their origin. So first step is to clarify whether jet is originating from AGN or star formation, and this will lead to my next project, which I'll be doing at University of Oslo. So this is to understand the jet, and the next step comes to understand their effect on the star formation, right? Then only you can look into this redshift evolution. Though these are close by sources, then I'll be moving to the little higher range of redshift. So with at University of Oslo, then I'll be investigating the molecule, then UV star formation, then with millimeter the molecular gas,
and try to see, well, I'm trying to collaborate and extend it to the higher redshift. So the overall impact would be try to answer some of the questions which are shown in 2 plots. I mean, this is what I wanted to say. I am not sure how much I have conveyed you people. Whatever, I mean, yeah, so at least you know that there can be something called dual AGN. There can be some impact on star formation during mergers, and some of the interesting results, and decline the presence of double peak with correlation with double peak with dual AGN. I have studied 10 galaxies with UVIT, again finding some interesting results. And next is that using GMRT, I have started studying this low power AGN to understand their jet. And in future with ALMA, hopefully I'll be investigating the molecular gas to understand the overall impact. This is what I wanted to say. Thank you.
Thank you. Okay, so thank you for a very nice overview of the observational studies that are going on in India. This was the first outside seminar. I think this was seminar in 2 years. So
okay.
We managed to give a very nice overview of the subject.
Yes.
So we should good luck for your post. So ideally, what we should do is when somebody asks a question, you should repeat it so that people who are on online can hear.
Okay.
Hear it.
Sure.
How do you decide which side might come from other people?
To look for? No, as I said that I start. Oh, so how do I find, or how do I decide which part of the sky to observe? To look for dual AGN or anything? Dual AGN. So that's what I said, that if you just ask for telescope committee that I want to look for this part of the sky for dual AGN, they won't give you time. What we have done, we have started with some indirect signature. So you have, suppose this SDSS spectra, so SDSS telescope has spectra of say like several thousands of lakhs of galaxies, and this spectra, some of this spectra has double peaks. So you start with double peaks and then put some criteria and say that okay, is double peak some separation we have put, say the velocity separation 400 km per second, though not very concrete, and then you say that this double peaks can be due to presence of 2 AGN, and then you put a small number of sample galaxies, and that's how you observe.
So basically, just to clarify, for those who do not know how observational times are given, so there are some instruments which are highly oversubscribed, like for example the HST, the Hubble Space Telescope, PLA, which she has used widely. So typically there are proposal cycles. So observers have to submit a proposal. The proposal is sometimes at the level of a research project proposal, and you have to show that you have done your homework. And if they allocate you time, there is a very high probability that with that time, the observation that you make will result in a few questions. Because that is important for the observatory, because it takes humongous amount of funding to make them, keep them running, right? They have to justify this with a number of papers. So often, I know of very many good senior astronomers whose proposals are also rejected. So getting your proposals funded in the most advanced telescopes, both government spaces in the world, is not a very easy job.
Yeah, so that's how. So you have to put, give them some concrete criteria, or as Rubinur said, that you have to have your homework done well, and it's very competitive. So it's not what you have done; it's like what others have done and where you are better than them. So now suppose I'm reviewing, so I have submitted this ALMA proposal, and if you submit one ALMA proposal, in reverse, you have to review 10 ALMA proposals. And this 10 ALMA proposals is not that you are just putting a number. So they have asked me to, give this what's called comparative number. So compare one proposal with respect to other 9. Which one is the best? So this is how, the competition goes like this, that, I'm also experienced, I have started for GMRT reviewing the proposal. Now for the ALMA I'm doing. So, yeah, it's a bit
tough and competitive field, but obviously everyone is trying. Yes. Have I answered your question? Okay.
Can I ask you a question?
Yes.
Sure, go on, go ahead.
I think I have one more question. So, what are the estimated ratio of the masses of these two cores that you have detected, at least for your own detection?
My own detections, the black hole mass are almost similar. So, as far as I remember, this ratio was around 1.1 or something like that.
Almost equal.
Almost equal.
So then I have actually a follow-up question. I mean, how do you make sure both belongs to the same galaxy, not someone that is behind one of them?
Yeah, so this comes from, so you are talking about this Markarian 212, the last system I have showed?
Yeah, well, let's say you detected
yeah.
dual,
So that,
right? How do you know they belong to the same galaxy, but not some other galaxy just behind the first one?
Yeah, that is true. But now, suppose for the systems I have, so the systems I have the separation more than 3 arcseconds, and the individual core have a spectra. Suppose for Markarian 212 with HCT, Himalayan Chandra telescope, we have obtained the spectra, we have reduced the data, and then estimated the redshift from velocity, the absorption line. So if your redshift gives you the similar scale, then only we are confirming, because everywhere there is a chance, like what Preeti has detected, the sub-arcsecond, sub-parsec binary AGN, there is still a chance that it can be a projection. The only factor is that what is the fraction of that. So yeah, we have spectra for individual cores, and those are close by system.
But how far are they all located? I mean, as for the redshift estimate. How far in terms of, let's say, typical size of the galaxy that you have, like they are separated by 1/10 of the galaxy size itself?
Oh, you were asking about
the separation of these two galactic movements.
So this in KPC scale, they have 6 kiloparsec separation. The other one has 10.6 kiloparsec separation.
Okay, thanks.
Anybody else have some questions? Yeah. Would you like to comment about yesterday's image?
Okay.
So do you think such things are possible for active galactic nuclei, dual galactic nuclei also? In principle, it should be, because
the fact is, obviously, the yesterday's discovery, I was on train and I need to read. So in group, there are like hundreds of messages that who are thinking what and what can be true and what can be true. But technically, things can be possible, because if we are believing what we are looking with or getting from GMRT or VLA, those are the, so here the fact is that you are going to the higher scale, right? And then, what is the reason that you won't believe? Because I heard that there is a paper there is a paper which says that it can be artificial to like the image, but I have to read that paper too. That, people have that thought. But my point is like, why can't you detect supermassive black hole, or active, basically the active supermassive black hole, if you can achieve that resolution? So, I don't find the reason that to deny, because
is there any other instrument other than EHT that can do that, or it's the only instrument, because the large space time is the only instrument that is suitable for resolving?
No, so this EHT is the only one, but EHT is combining all the dishes over the world, right?
The consortium, which is combined.
Yeah.
GMRT also contributed to that?
No, so but GMRT has, I heard that GMRT has started participating in VLBI. So you can't just
the specific wavelength.
So first you need to check that, so you have to have that correlator system, that whether telescope somewhere in Europe and at this from GMRT real-time correlation can happen or not. So I heard that people have started working on it, and maybe in future GMRT will also be part of that. So it's just that obviously the frequency range. So if GMRT can be part of that, because the most of the VLBI system, so this all EHT and whatever VLBI, all of this we call as like this comes through interferometry, right? So most of the telescopes have frequency above 1.4, but there are like several billions of systems which are which has low luminosity. So 1.4 maybe they don't have any emission, but 325 they can have emission. So GMRT has ability to observe with at 325 610. So in future maybe this can happen, and one can find more such systems. Yes.
With the advent of LISA, I think active dual active reactive nuclei can be transformed. You see get the adaptation.
Yeah. So I also have similar thought and similar understanding that with LISA, and we are hoping that with LISA, if we can have some of the very concrete, because as Rubinur said that these are very, very demanding, and you have to spend a huge money on this. So people have started working on it. I know that some of the groups have even are trying to look into this dual agent, very close by dual agent candidate, binary candidate, and even through EHT, if in future it can be possible, they will try to look into it. And with LISA, obviously, people will be looking for those systems where it can look and then can say that maybe the merger has happened and things like that. So that is what I can comment. So EHT, what I have understood, that it is not that you can apply for any object. So time is such that now they are trying to make the template. They will be giving you certain objects, and then you have to decide that with this object whether you will be able to do such science or not. So now what we are doing, we are selecting our sample and asking a telescope. Now telescope system like EHT, telescope people will be giving you the saying you that say these 5 sources you can observe, and then you have to decide that whether with these 5 sources one of the source can answer one of your question or not. So yeah.
Okay, I think let us close there.
Yes.
Thank you very much. We are very happy that that we are the first external institution that will give a seminar.
Yeah, I'm also happy.
And the first post-pandemic seminar that you're giving.
Yeah.
Thank you for stopping by.
No.
And welcome to visit us again when you're passing by tomorrow.
Yeah, sure. I'll be doing that. So now I have to explore either and see that.
The students